All right, so our group activities are going to involve solving a bunch of integrals. Okay, so for this first one, I have a composition, and the inside function, the function under the square root, is x cubed plus 1, and its derivative is 3x squared, which an x squared also shows up in my integrand. So a good option for you would be x cubed plus 1. So then we calculate du dx, and we get 3x squared, and solve for dx, and we get du over 3x squared. So this integral becomes the integral of x squared times the square root of u times du over 3x squared. And then your x squareds are going to cancel, so I have no more x's left in the integral. So this is the integral of 1/3, because that 3 is in a denominator, so it's 1/3. And square root u is u to the 1/2. And now I can just use the power rule. This is 1/3 times, add 1 to the exponent, and I get u to the 3/2. And then I'm supposed to divide by the new exponent, which is the same thing as multiplying by its reciprocal. So I have a plus c on there. And then lastly, I replace my u's with an x cubed plus 1. So this becomes 2/9, just multiplying the 1/3 times the 2/3. U is x cubed plus 1 to the 3/2 plus c. Okay. Similar approach in the next one. I have a composition, so I'm going to try again letting u be x cubed plus 1, which means dx is du over 3x squared. And when I plug in, I get the integral of x times the square root of u times du over 3x squared. Now the problem happens here because my x's don't all cancel. I still have an x in the integrand. This is the integral of 1/3 square root u 1 over 3x square root u du. I have u's and x's, so this one turns out to be the impossible one. We can't solve this using u substitution. Okay, the integral of e to the 5x plus 7. I have a composition that's e to some stuff. The inside of a composition is always a good option, a good first guess for you. So I'm going to let u be 5x plus 7. So du dx is 5. Solve for the dx, and I get du over 5. Plug back into the integral. I get the integral of e to the u times du over 5. So I'm going to pull my 1/5 right out of the integral. This is 1/5 the integral of e to the u du. Now I take an antiderivative. The antiderivative of e to the u is e to the u. Lastly, plug in my u, 5x plus 7. So this is 1/5 e to the 5x plus 7 plus c. Okay, next one, the integral of 9 to the x times the sine of 9 to the x dx. So I have a composition, the sign of some stuff. The inside of a composition is always a good candidate for a u substitution. And the derivative of 9 to the x is 9 to the x ln 9. And I have another 9 to the x that shows up in my integrand. So I think 9 to the x is a good candidate for u, because then du dx will be 9 to the x ln 9. Solve for dx, and I'm going to get du over 9 to the x ln 9. But 9 to the x is u, so let's see. This is going to be the integral of u times the sine of u times dx, which is du, over 9 to the x, that is u. So this is u times the ln of 9. So what cancels? U over a u here. And then the ln 9, it's in a denominator. I'm going to pull it right out of the integral. So this becomes 1 over ln 9. times the integral of sine of u du. This is 1 over ln 9 times the antiderivative of sine, a function whose derivative of sine is negative cosine u plus c. And then lastly, replace the u with 9 to the x. So this is 1 over ln 9, make that negative, times the cosine of 9 to the x plus c. Okay, here's a fun one. Tangent x, I want to find an antiderivative of tangent x. You should know what this is because you memorized it for quiz 2, but now we're going to derive it. Okay, so I'm going to rewrite tangent x as sine over cosine. And now I'm going to do a u substitution where I let u be cosine x. And that means du dx. The derivative of cosine is negative sine. So I solve for dx, and I get du over negative sine x. Now I go up here, and I plug everything in. So this is going to be the integral of sine of x over u times dx, which is du over negative sine of x. So that's nice because now my sine x's cancel. I still have a negative, so I'm going to pull that out of the integral. So this is negative the integral of 1 over u du. Now the antiderivative of 1 over u is ln u, so this is negative ln u plus c. And last, replace the u with cosine x. Negative ln of the cosine of x plus c. Okay, now I'm going to do some definite integrals where I have bounds. So it says to do the indefinite integral without limits on the side. So over on the side, I'm going to calculate my antiderivative. So I just need to do the indefinite integral of e to the sine x cosine x dx. So I'm going to let u be sine of x because it is the inside of a composition, and its derivative, cosine x, also shows up in the integrand. So du dx is cosine x, solve for dx, and I have du over cosine x. So when I plug into my integral, I get the integral of e to the u times cosine x times dx, which is du over cosine x. And my cosines cancel. This is the integral of e to the u du, which is e to the u plus c. Last step is to replace the u with sine x. So this is e to the sine of x plus c. So I now know an antiderivative, the general antiderivative of e to the sine x cosine x. So now I can use the fundamental theorem because I now have an antiderivative of the integrand. So the integral from 0 to pi over 2 of e to the sine x cosine x dx is the antiderivative of e to the sine x cosine x dx, which is just e to the sine x evaluated from 0 to pi over 2. Just take the antiderivative and evaluate at the bounds. So first I plug in pi over 2. This is e to the sine of pi over 2. Then I plug in 0, e to the sine of 0. The sine of pi over 2 is 1, so this is e to the first. The sine of 0 is 0, so this is e to the 0. E to the first minus e to the 0, that's e minus 1. Okay, this one is broken down into steps to help you. So the integral from 0 to 2 of x squared over x plus 1. I start by working on an indefinite integral where my u substitution is u equals x plus 1, which means du equals dx. So this becomes the integral of x squared over u du. Just replaced x plus 1 with a u, and dx with a du. So this doesn't look great because I still have x's and u's in the integrand, but I can fix it by solving u equals x plus 1 for x. So x equals u minus 1, which means that x squared is u minus 1 squared. So I can now plug in to the integral I just had, but instead of x squared, I'm going to put u minus 1 squared over u du. So to solve this, I'm going to multiply out the numerator and divide u into each term of it. So this becomes the integral of u squared minus 2u plus 1 all over u du. Then I'm going to divide u into every term of the numerator. So this becomes the integral of u squared over u is u. Negative 2u over u is negative 2. And then 1 over u is 1 over u. du. Now I can integrate term by term. So the antiderivative of u is u squared over 2. The antiderivative of negative 2 is negative 2u. And the antiderivative of 1 over u is ln u plus c. Last but not least, convert the antiderivative back to the variable x. So now I want to replace all of my u's with x plus 1s and evaluate at the bounds. So I'm going to have x plus 1 squared over 2 minus 2 times x plus 1 plus the ln of x plus 1. And I want to evaluate all of that from 0 to 2, the original bounds on the integral. So let's see, if I plug in a 2, 2 plus 1 is 3, squared is 9, so I have 9 halves. And then 2 plus 1 is 3 times 2 is 6, so minus 6. And then 2 plus 1 is 3, so plus ln 3. And then I'm going to plug in a 0, so I get 1 half minus 2 plus ln of 1. And I simplify, so 9 halves minus 1 half is 8 halves, or 4. Negative 6 plus 2 is negative 4. And then ln 3 minus ln 1. So my 4's cancel. And the ln of 1 is 0, because e to what power gives you 1? 0. So this is just the ln of 3. All right, and then this last problem, again, I'm going to start by doing the antiderivative on the side, and then I'll use the fundamental theorem once I know the antiderivative of the integrand. So I want to integrate 7 over 4x minus 3 dx. I'm going to let u be 4x minus 3. du dx then is 4, which means dx is du over 4. So my integral becomes the integral of 7 over u times dx, which I replace with du over 4. So I have 7/4 as my constant. I'm going to bring it out of the integral. 1 over u du. So this is 7/4. The antiderivative of 1 over u is ln u plus c. And then finally plug in the u. U was 4x minus 3. Okay, so now I know the antiderivative of the integrand, so I can come back to my definite integral, write down an antiderivative. Typically, we choose plus c to be 0 because we can choose any plus c we want for the fundamental theorem. You just need any antiderivative of the integrand. And then I'm going to evaluate from e to 2. So that means first I plug in a 2 for x, and I get 7/4 times the ln of 8 minus 3 is 5. And then I'm going to plug in an e, so I get 7/4 times the ln of 4e minus 3. And that's pretty much the answer. I'm just going to factor out a 7/4, but you don't have to. This becomes 7/4 times the ln of 5 minus the ln of 4e minus 3, which is just a number. It tells you the exact area under this curve between e and 2. Okay, last one. The integral of 1 over radical 16 minus x squared. We've got several hints we can follow. The first thing we should notice is that the integrand looks similar to the integrand that gives us arcsine of u plus c. To make it look exactly like the integrand for arcsine u, I need this 16 to be a 1. So I'm going to factor out a 16 in the radical. So pull out a 16 so that when you distribute it, you get 16 minus x squared. Now we pull that 16 right out of the integral, right? So pull it out of the radical, because the square root of 16 is a 4th. So that ends up being 1/4 outside the integral. And then we have 1 over radical 1 minus x squared over 16. Okay, so I'm going to rewrite x squared over 16 as x over 4. So let's just start from here. 1/4 the integral of 1 over 1 minus. If u is x over 4, x squared over 16 is u squared. And that's all under a radical. And then instead of dx, if u is x over 4, then du dx is 1/4, which means that dx equals 4 du. So instead of a dx, I put a 4 du here. So now my 4's cancel. Oh, I think I messed this up. Okay, I don't think I messed it up. This is the integral of 1 over radical 1 minus u squared du is arcsine u. So this is arcsine u plus c. But then I have to plug my u back in. So this is the arcsine of x over 4 plus c.